tour of the universe, mostly the solar system and a little beyond, using software called OpenSpace. And I feel like, so if you can't hear me, let me know. And I actually can't even see my notes, but hold on a second. Okay. So, I'll talk a little bit about my research, but I'm going to start here. I study forming stars. And can you all see what's up here? Yes? Okay. So I'm starting here with the solar system, and everything you see here, let me see if I can do this. Okay. Yeah. I can't, but hey, sir, I actually can't hold this and drive at the same time. You can't. What? Well, I need some help with the mic then, because I can't actually do this and hold the mic at the same time. Okay, maybe this somehow. Sorry, hold on. Thank you. All right. Okay, so, good? Better? All right. Thank you. All right, good. So everything you see here, this is software that I'm going to use. It's Flying Through the Universe software called OpenSpace. And everything you see is accurately placed. You have the stars here, the star field, and you have the planets all in the right position. And it is free and open source, so you can download it and use it. Although I will say it's still in beta phase. It's a NASA-funded project. And so you might need a computer like this, like an Alienware. It doesn't really work on a phone. But I'll tell you the website. It's OpenSpaceProject.com. Okay, so what you see here is the solar system. And as you saw in trivia, we have 8 planets. And so Pluto is not a planet. And all the planets formed in a disk, a protoplanetary disk, 4.5 billion years ago. And you can see the remnants of this disk by the fact that all the planets are in the same plane. And here I'm moving around and showing you that, all these planets in the same plane. And we actually have some remnants of that disk still, and the remnants of planet formation still in our solar system, and I'll turn some of those on right now. The cool thing about OpenSpace is that you can turn on data sets and manipulate the data sets yourself. So I'm going to turn on, first of all, I'm going to turn on the Trans-Neptunian Objects, which are actually comets. And these are comets. They have kind of like crazy orbits. They're far away from they're far out in the solar system. And these lines show the trajectory of some of these far away comets. But a lot of them do fall in this sort of disk plane. You can see the majority of them here. These are just some of the comets. These are these outer icy objects that are in the outer solar system. And when they come in close to the sun, you see their beautiful tails, and like Halley's Comet is a famous one. And they're out in the outer solar system, and they're actually right around, a lot of them are where Pluto is. And so Pluto and all its friends are out in the outer solar system, and not actually planets, but these Kuiper Belt objects. And as we go into the inner, so I'm actually going to turn on now I'm only going to give you, this is a short tour, but I'm going to turn on some of the asteroids. And you can see how close in they are. I'll turn on a couple of them, just these little. So as you go further in towards the planets, now we're zooming in, and it's a little choppy because the asteroids are actually a lot of data. And here are a few of the asteroid data sets that I turned on. So you see here, these are the Jupiter Trojan asteroids. These are the inner main asteroid belt, the outer main asteroid belt. And what you can see is that they also orbit the sun, and they orbit between Mars and Jupiter. The cool thing about the Trojans is that you can actually see spaces here caused by the planet Jupiter. So Jupiter, I'll actually turn on, I think this is, yeah, there's Jupiter. I just made it bigger. So Jupiter causes these spaces because it's so massive. Hopefully you got that right. It's the most am I allowed to say? Good. All right. I win the prize. It's the most massive planet in the solar system, and it causes these spaces in the asteroid belt because of its gravitational pull. And it also deflects. So thank you, Jupiter, because without Jupiter, we would have a lot more asteroid hits to the Earth, and it probably has saved us from some pretty apocalyptic events on Earth. Comets go into Jupiter, so do asteroids. It vacuums up and mops up all of these objects that can come near our planet and destroy life and cause problems, but also possibly have been the source for life in our oceans. And so we also like asteroids, and I'll talk a little bit about impacts in this talk, is that without asteroids, we may not even have the ingredients for life on Earth, and we may not even have, I'll zoom into Earth a little bit here, we may not even have our oceans. Here's Earth, and here's just Earth with some of the asteroids and comets. And now I'm actually going to turn these, well, I'll leave these on for a second, but I'm going to turn on a data set now, these blue ones, and I'll turn off the inner and outer, and and here, and the Trans-Neptunian. So everything I'm showing now are the potentially hazardous asteroids. These are the asteroids that could cross Earth's orbit and hit us. And many have hit us, and many will hit us again. The larger the asteroid, the more planet-destroying the asteroid, the less likely it will come. I'm actually going to turn off, I'm going to reduce, there we go. The less likely it will hit Earth, but they do come. And we know that asteroids have caused extinctions, right? 65 million years ago, what went extinct? Everyone remembers? Dinosaurs, exactly. So let's we'll go down to Earth, because this talk covers some other stuff. So let me go to, in OpenSpace you can actually make bookmarks, so I've done that. And I'm going to go to Meteor Crater, one of my favorite places to visit, and I think it's on, Meteor Crater is here. With OpenSpace, it does draw in actually, let's see, Meteor Crater. It does pull in data sets, so it takes a second to do that, so we'll just give it a minute to load in my bookmark. And everything in OpenSpace, as I said, it is data-driven. So all of the placement of the comets, the stars, the planets, all the data sets are real, and this is been put together by the American Museum of Natural History, who leads this project. So everything in here, let me just make sure I'm in the right spot here. No, I was not. Hold on a sec, there we go. All right, so there's my little bubble. Okay, so I will locate Meteor Crater. Here we go, and back to Earth. All right, so Meteor Crater, has anyone been to Meteor Crater? This is in Arizona, and it's near the Grand Canyon, this beautiful canyon that actually, before we go to Meteor Crater, let me go to the Grand Canyon, because I like the Grand Canyon. All right, here's my other one. So the Grand Canyon is pretty recognizable, and it is about 220 miles long. It is our biggest, most spectacular canyon on Earth. It represents millions of years of Earth's history. And it is really a spectacular feature, and probably several of you have been there. If you haven't, I highly recommend it. It was made by the Colorado River. So we love the Grand Canyon. We think it's amazing. We live on Earth. You can use OpenSpace to drive around if you can't get to Arizona. But it turns out that on a planetary scale, the Grand Canyon is pretty puny. And it really pales in comparison to a canyon on Mars, which we're going to go to as well. And part of what we look at on Earth and other planets as planetary scientists and astrobiologists is comparative planetology, meaning what can we learn about our planet and other planets by comparing these planets. We all form from the same disk of material. We all form from the same stuff. And so that's why we search for life beyond Earth. We search for life in space because all of the molecules are there. And I actually left on the Earth crossers there. You can see these in the blue streaks. And so when we explore space, we're thinking about not only is there life beyond Earth, but also how did life, will we survive on our own planet? And how did life begin? And is there life elsewhere? And these are big, big questions that we don't have answers to, of course. But this is part of the search. And again, one of the things that we're interested in question is how space has influenced, you know, how did Earth start, we know how it started, but we don't know how life got here, and we don't know how our oceans got here, and it's quite possible that impacts have brought us the materials we needed to have our oceans and to have life. And Meteor Crater is a very small crater, but it's very well preserved. It's in Arizona, not far from the Grand Canyon, as you probably just saw. You can do both if you visit Arizona. It's not hard to visit both. And if you zoom down, this canyon formed 50,000 years ago in the Colorado Plateau. And right around this time, I have a few pictures to embellish the talk. So right around this time, there were woolly mammoths in this area, in the Colorado Plateau, and there was a giant sloth. And those are the only two examples that I have. But it was much greener, and there are all these really cool Ice Age mammals. And these are both extinct. There were saber-toothed cats, although I'm not 100% sure they were in the Colorado Plateau. But they were all here, and they would have possibly experienced this impact. Now, 50,000 years ago is not that long ago, so this certainly wouldn't have brought us our oceans or contributed to the start of life, which happened at least 3 billion years ago, probably longer ago. So within the first billion years of Earth's history, we think life started. But this is a very well-preserved crater. And it's one of the craters, we have about 130 or so preserved craters on Earth. We lose a lot of our craters because of weathering and erosion and rain and our atmosphere, which protects us. But we also don't have all the lovely craters that we could have. And most of the meteors and meteorites, most of those asteroid explosions, they happen over the ocean, right? 75% of the Earth is covered in water. But we go to Meteor Crater, and a lot of planetary geologists explore this crater. The Apollo astronauts were trained in this crater, in this very crater, to try to understand if what was going to be on the moon. So they didn't know if the moon had impact craters or volcanic craters. And so the Barringer crater was used to train the Apollo astronauts in the 1960s to try to differentiate. And it turns out most of the moon is actually impact craters. And the moon, we're not going to go to the moon today unless you want me to later, but I wasn't planning on it. But the moon is a historical relic of this history of bombardment in our solar system. About 500 million years after the formation of the Earth, there was this period of late heavy bombardment when all that remnants and all those asteroids and comets were hitting. There was a lot of leftover stuff. And the moon preserved that, as well as the planet Mercury, a very small planet. I hope you all got that. I didn't say anything. Anyway, this is Meteor Crater. So we're going to talk a little bit about astrobiology in this talk, and part of that is what kind of life do you think we're going to find in our solar system? And it turns out we're probably not going to find the life that interests most people, and that is aliens and monsters and things with big heads and all of that. But we're probably going to find extremophiles, these microbes that live in really extreme environments. And we use environments on Earth as analogs to try to study, what is the kind of life that could live in space, that could be in space. And one of those places is a really cool spot in Yellowstone, again in the west, the beautiful west of our United States. And I'm going to zoom into this area, Grand Prismatic Spring. It's kind of small, so I have to wait for it because I can't find it by eye. There it is. And here we go. So Grand Prismatic Spring is in Yellowstone National Park, and it's got all these spectacular colors. And it's something I can show you. Whoops. Hello. Stop. It's something I can show you with OpenSpace because a lot of the environments. Why are you so OpenSpace likes to move. Hold on a second. Okay. Hold on a minute. Oh, I have rotation on this. Okay, so in Yellowstone National Park, you can visit Grand Prismatic Spring. The colors come from microbes, extreme microbes, bacteria kind of things, that produce these enzymes that enable it to live in extremely hot environments. And so this is one of the hot springs. Sometimes you read people fell in, like you don't want to do that. There's a path you can walk along, but a lot of visitors don't do that and they fall in, or they try to go in, I don't know. We're not the smartest species, if you ask me. But This is one example of the type of life. We didn't actually know that there was extreme life like this. These were only discovered in the last 50 years or less, 40 years, that there's extreme microbes that can survive hundreds of degrees. And not just that, they live under the ocean, they live encased in ice, they live in rocks under the mine, in these big, deep mines, miles below the surface of the Earth. And so astrobiologists think this is the kind of life we're going to find. Maybe microbes like that live in Grand Prismatic Springs, maybe in Europa, in the oceans of Europa, or possibly still on Mars, because Mars has some water underneath the surface still, we think. So this is the kind of life we think we're going to have, and I think if there's time I'll end in another location, but for now I'm going to go to a different spot and talk a little bit about how we observe beyond this planet, and probably a lot of you know how we do that. But I'm going to go to Mauna Kea, which is in Hawaii, and it is on the other side. Here we go. And it's still dark, so I'm going to turn it on. You can, what I love about OpenSpace is you can change the day and night and make it as light as you want. And let's go. There we go. All right. So Mauna Kea is on the Big Island of Hawaii, and it is where 13 observatories are. I'm actually going to turn my bubble off. Okay, so Mauna Kea is a shield volcano. It is the only volcanic island of Hawaii. The active volcano, all the islands of Hawaii were made by volcanoes, and they all go over a hot spot of Earth. And that's one great thing about Earth, right, is that it has plate tectonics and it has volcanism, and that keeps us part of our habitability, right? Part of what makes the Earth habitable is all of its dynamic processing. We have an atmosphere, we have a magnetic field, and we have volcanism. And a great representation of that volcanism is Hawaii. On the other side of this island is Kilauea, which actually still erupts. But what you can see here, Mauna Kea doesn't erupt still. It's still considered slightly active. It could erupt. And it is a shield volcano. So it's the type of volcano that we also see on other planets like Mars. And you see these little anthills. These are actually little parts of that shield volcano that you can visit and walk along. It's really beautiful to go there, and it's a really excellent place for astronomy. It is 14,000 feet in elevation, and it is high, it's dry, it's above the marine layer, which is a lot of the atmospheric water which we want to get rid of in astronomy. And so the research I do is I look at forming stars, and I want to see the gas around them. So like that disk that I mentioned for our solar system 4.5 billion years ago, a lot of stars now still have these disks. And so we can study these disks to try to understand planet formation in general, because we have a lot of exoplanets, and also understand how our own solar system forms. So I use this telescope here. This is the infrared telescope facility. And I'm going to pause a little bit with OpenSpace and show you a couple of images from this observing. So typically I go to the mountain and I observe in person, and you can stay in this little visitor center down, I think it's actually down around here, called Halepuaku, and you stay at about 9,000 feet, and then you drive up to this telescope and you observe. And so some of the pictures I took, this is what the facility looks like. It's like a glorified lodge. It is a lodge for astronomers to stay, and the people who work on the mountain and work in the parks. There's a really endangered plant called the Mauna Kea silver storm. I would say it's my favorite plant. It survived. It actually was eaten up a lot by introduced goats and sheep and cattle and stuff to the mountain, and so it was really decimated, and they're trying to bring it back. But unfortunately, they have these little gardens, this little enclosure you can go in, and you wipe your feet here, and you go in, you walk around, and you can visit these plants. They last about 15 to 40 years, and once they flower, they then die. So it's very sad. But you can see some of them flowering, and then you know that this part of the plant is going to die. But it's still the leaves here survive the harsh environment of Mauna Kea. So Mauna Kea has, excuse me, and it doesn't get a lot of precipitation, as you might imagine, and it can get very, very cold. And so the Mauna Kea silver sword, while still a pretty, we don't expect anything as advanced as this on Mars, for example. It's a type of life you sometimes feel like you might see on Mars, some kind of scrubby little, although I don't mean to insult it like that, but it is kind of a scrubby little plant. But it has these beautiful silvery hairs on their leaves that hold in water, and so it's adapted for this really harsh environment. And then you drive up and you see this beautiful, the clouds, and you're driving up into the atmosphere, it feels like. And so you get to this, I use this one of 13 facilities on Mauna Kea, the infrared telescope facility. And later I'll talk a little bit about Voyager, a mission that's going out to the stars, literally. Hopefully you got that star right, by the way. I thought this was a very good trivia for this talk. And this telescope was built to support Voyager in the late 1970s. And now we use it for astronomy, for other types of missions. It's about a 3-meter telescope, and just a couple of pictures. Inside, it's a pretty massive telescope, so we don't actually peer through an eyepiece. We use a computer, but you can, you can visit. You can go inside and watch them prepare for scale. That's me. I'm about 5'5". You can walk around the dome. It's cold, obviously. And I just put this in. If you want to know, light comes in, it bounces around to a bunch of mirrors. This is a reflecting telescope, and then you get your image on a CCD, just like a camera, but it's actually, what we want is the spectrum, it's the molecular information. So we take the image and we put it through a code, and then we get the spectrum. And this is me, just probably a little spaced out because it's like 14,000 feet, and I can function, but it's a little high. We have support astronomers. He's actually the telescope operator, and I'll sit here and he'll sit there and he'll monitor the weather, and if there's any problem, they close the dome, like fog. You have to be careful with these very expensive telescopes. This is a picture I took of a forming star. So these stars are everywhere. There's stars all over the galaxy, and we have billions of stars in this galaxy, and there are hundreds of billions, there are about 400 billion galaxies roughly, and about that many stars in each galaxy. So that begs the question, it's probably possible, there's an Earth-like planet just like us, but everything is so far apart. But it still is worth exploring. So what I'm looking at is not looking for life, but I'm looking at these stars in the stages of formation right when we were forming, around 4.5 billion years ago. And this is a massive star, looking at chemistry around these stars, and this line is the telescope, and these are the winds blowing off the star, and you see these like bipolar winds coming off, so it's really cool. I don't actually take any science out of the picture, I just like the picture. So I took the picture, and then the actual science, it is a binary, it's hard to see. There's 1 and 2 here, and stars often form in multiples. And so we are unusual that we have 1 star, we have 1 sun, but it's probable that the sun kicked out a companion, or something happened that we only have 1 star. But there are many planetary systems with more than 1 star. In fact, that's more likely that you're going to have more than 1 sun. This is what data look like. I'll just show because I think it's pretty cool. This is energy here, this is wavelength, and what I'm looking at in the infrared are lines, and these lines are the data. This is carbon monoxide, and I'm looking at the chemistry of carbon monoxide for lots of reasons that I'm not really going to talk about too much today, but I'm interested in carbon, that's life as we know it, and oxygen as well, and the CO, carbon monoxide, is really important for chemistry in these systems. Oh, that's my next stop. Okay, so that's Mauna Kea, and now, hold on. Oh yeah, okay. So now we're going to leave Earth. I hope that's okay. We're going to go to Mars. And Mars is the next stop, honestly. Let me see something here. All right, so I'm going to go to Mars. And Mars is where we're sending, as you probably know, where we're sending all of these rovers and missions. And it's our next stop for astronauts after the moon. Chances are this is not going to happen. The next stop is not going to happen for decades. because it's very dangerous. What I just flew through, that space I just flew through, is full of radiation and full of dangers and all this stuff that NASA will send astronauts to. But what I'm going to show you just real quick, I'll show you Dallas Mariners. Hold on a sec. Mars. Oh, there we go. Okay, so it's still dark. The day on Mars is roughly about an Earth day. It's a little bit longer, but we're going to wake it up. So here you can see for scale, Mars is a bit smaller than Earth, but here you can see for scale, this is Valles Marineris. It's about 2,200 miles long, and that's compared to the 200 miles length of Grand Canyon. And I can turn off this bubble because Valles Marineris is pretty obvious. And what's interesting about Valles Marineris, it didn't form by water flow. It probably formed by some rifting up from the planet. So we don't think astronomers don't think, or planetary astronomers, actually, I should say, or planetary geologists. I'm going to turn off while I ramble. I'm going to turn off the Earth crossing, and I'll turn on the Mars crossing, so you can get a sense of what it's like on Mars. These are the asteroids that could hit Mars, that will cross Mars's orbit. So I'll turn those on so you can see what that might look like. So with OpenSpace, with these data sets, all of the data that you see on Mars that's visualizing Mars is from the Mars Reconnaissance Orbiter, which is now orbiting Mars still for decades, for a couple decades, about 2. Has been orbiting Mars, taking all the amazing data, all of the visual data that we see. And it has to load in. It actually looks pretty high resolution. With high-speed internet, it'll load in a second, and we're going to go to another crater in a minute, so hopefully you won't be too disappointed by this. But Valles Marineris is the largest planetary canyon in the solar system. It dwarfs the Grand Canyon. The Grand Canyon is a tiny little speck compared to Valles Marineris. But it's very interesting, and it tells us a lot about the different geology. As opposed to forming, like 5 or 6 million years ago, which is when Grand Canyon formed, Valles Marineris formed about 3.5 billion years ago, when the planet was forming. And keep in mind, too, when Earth's life was starting about 3.5 billion years ago, Mars was dying. Mars lost its water, it lost its atmosphere for the most part, it lost its magnetic field. So while Mars was habitable 3.5 billion years ago, it didn't stay that way. And we don't know why, and that's why we're sending so many missions there. We don't even know if life started. Life starts quickly. It started fast on Earth. It probably could start fast on Mars, but it didn't really survive. And the atmosphere, by the way, is still on, so that's why it's a little fuzzy. But let's go. We'll stop here. There's another shield volcano. Help me on time. Okay? Okay. I'll just, I don't know how exciting it is. You know what? I'm going to skip the volcano. The volcano on Mars is kind of boring looking. But let's go to Jezreel Crater, because that's kind of interesting. Jezreel Crater is where we now have the next rover, Perseverance. We landed there. Humans landed another rover. I'm looking for it. There it is. It's dark there at Jezreel, so we're going to wake up whatever's there. So Perseverance and Ingenuity are there. Ingenuity is this little helicopter. It's pretty cool. So let me turn on the daylight. And we've got several rovers, you probably know this, right? Is that we have several rovers on Mars already, looking for past life, possible current life, although that would be more unlikely, and looking for, trying to understand the atmosphere. How did Mars lose its atmosphere? There's actually a satellite now doing that. And what kind of technology is necessary to send humans to Mars? And this is a very big question, right? Because everybody wants to send astronauts to Mars, or a lot of people do, and there are plenty of astronauts who would go even on a one-way trip. Many signed up for these missions, but NASA will not send astronauts on a one-way trip. So let me get back to Jezreel. Hold on a second. I think I lost it. Oh, because I'm back on Mars. I have to get back to the crater. No. Okay. So I'm going to talk a little bit about Jezreel. I gotta be able to recognize it. Let me load in a second. Oh, here we go. So there's a lot of evidence for water on Mars, past water on Mars, and Jezreel is a really great example of that. And while it's loading, I just make sure I can get back there. Oops, oh, excuse me, I made a mistake. Let's fly back. Nice thing about OpenSpace is you can defy light speed and any kind of realistic space travel by just going back to where you started in 1 second. Here we go. All right, so there's Jezreel. So I'm turning on, what you see, by the way, I'll mention, these squares. This is actually kind of cool to show. I show my students about data sets. We have HiRISE as a camera on a Mars Reconnaissance Orbiter, and it takes some really high resolution data. And so what I'm showing you here, when you see it, sometimes these squares are the sections of data where we have high resolution. All right, so what you see here, this is Jezreel Crater, and if you zoom out, you can see kind of this delta much more easily. There's a river channel that goes through. There's an ancient river channel. So water, this is one of many examples on Mars of water flow, past water flow. Not now, there's some examples, some evidence that water currently can flow on Mars for short periods of time, but it evaporates or freezes very quickly. But this is Jezreel, so when it fans out like the Mississippi Delta. And this is a shoreline that I'm pointing to here. This is an ancient shoreline. And this is why Jezreel was selected as the landing for Perseverance. The Perseverance landed right about here. And this really beautiful shoreline that has microbiolites. So it's this material that is similar to, there's analogs on Earth of these microbiolites, meaning it's a mineral that could have formed from microbes, we don't know. And so it's possible there's ancient fossil microbes in Jezreel Crater. And I'll just get over them. And so Perseverance rover is there now, it landed, and what's super cool, I think, one of the coolest things about Jezreel is that, about the Perseverance mission, is that for the first time since the Wright brothers, which was in 1903, we have flown another powered flight. We have flown a powered flight on another planet. And so this was the very first time that the helicopter, the helicopter Ingenuity, this little helicopter, was stuck at the last minute, and JPL engineers didn't quite know work or any of that. It was stuck on Perseverance before it launched, and it has now conducted about 14 little flights, going up, 10, 20 feet, and traveling around. And this is the first powered flight on another planet and if you look at a picture, I showed this to my students, 1903, the Wright brothers with their crazy plane, now we're flying on Mars in 2021. So it seems like a long time, but by a universal scale, this is like 0 seconds, right? Because the universe is 13.77 billion years old, so we're now flying on Mars 100 or so years later, and that's pretty neat. And so you can, with OpenSpace, I like to show, these really great detail, these like beautiful formations of wind, erosion, and water, and you can fly around and go up and down these river channels. And it's a really amazing crater. So it's a crater within a crater. So one of those Mars crossing asteroids hit probably 1 billion or so years ago and made this crater, and inside that crater there's water came, and with water could be life, and that's why it was selected. So when we think about water and Mars, and everyone wants to go to Mars, we might consider terraforming, and what would that look like? And I like, this is a little close-up of this cute little helicopter drone. I show this to my students. This is like terraform. Maybe one day we'll drop our spacesuits, we'll get to Mars and have an ocean. And it's quite possible this will never happen because we can't even control our own climate. But what will it take to keep a climate on Mars? Right now we can't even get to Mars safely, but to actually terraform a planet so you can walk outside is something we don't know how to do. You have to control the climate. You have to make the atmosphere hold on to the atmosphere. Right now, Mars has no way to hold on to an atmosphere, and we're very good at pumping out the greenhouse gases, but not good about controlling it, and we can't even keep an atmosphere on Mars. So this is something, sometime in the future, maybe, but maybe not. So anyway, so that's Mars, and that's a little stop I was just going to make. Okay, so when we talk about life, I'm going to actually take us away from Mars and go to the next best place for astrobiology, and that is Europa. So these are the moons of Jupiter, by the way, in their trails, and I'll show Saturn more up close and talk about that. But we're going to pass by Jupiter, the biggest planet. But Jupiter actually almost became a star, and that would have changed our lives a lot, and who knows what would have happened then. So Europa is the next greatest place for astrobiology. It has these really cool cracks. It has a global ocean. It's smaller than our moon, but probably has more water than the entire Earth. Earth is in fact a desert. It has a 0.6% by mass of water. We just think it's got a lot of water, but it really doesn't. But Europa does. Europa has a global ocean, we think, and the Europa Clipper is going to go to Europa sometime in this decade and look around and probably not drill down the ice because that's hard to do, but at least explore the, try to get some more data on the ocean. Maybe drill down, but that's very, very difficult. But these cracks are when the ice breaks and the ocean comes up and there's brine and salt, and that's why you see it looks red. And it's possible there are these deep sea vents that are kept hot by Jupiter pulling on Europa, and it's quite possible that there's life down there. It would be like we never saw it, we don't know, but it's definitely the next best possibility, probably more probable than Mars. And so Europa is a stop we want to make. We know there's water there, and it's under the ice, but it's definitely got a warm and cold rock and water, and warm is definitely where you want to look for life in the solar system. It'll probably be microbial if it's there. Okay, so that's all we're going to say about, sorry, Jupiter. It's kind of boring otherwise, but I'm going to go to Saturn next, and just take you to one more little planetary stop. So Saturn, a lot of people love Saturn because of its beautiful rings. Sometimes they call it the jewel of the solar system. But here you can see, what I'm showing here is what you can see, what's cool about Saturn is that the moons that are close to Saturn follow the plane of the rings. And so you can see that right here. The moons that are farther from Saturn are less gravitationally bound, so they're kind of all over the place, like we saw the comets. So this is a little bit like a mini solar system and follows this kind of disk. So Jupiter also has moons like this, but Saturn is really spectacular. And inside the innermost part are these rings. So you have the moons out here, and then you have these beautiful, beautiful rings. A lot of them are imaged by the mission Cassini, and there are also these really cute little moonlets in there. They're all little dust grains that probably formed with Saturn. Saturn is a very large planet. And Cassini took all of these gorgeous images of the rings. And so Saturn in its own right is really spectacular. And we're going to actually, for astrobiology, the most interesting part of Saturn is the moon Titan. And Titan is interesting for two reasons. Here it is. We actually landed on Titan. We landed a probe in 2005. Part of the Cassini mission had a little probe called Huygens. And we knew that Titan was interesting. We knew that Titan had, from telescopic data, had some interesting features, and we knew that there was something going on. It has a very thick nitrogen atmosphere, much like the early Earth. So that's the first reason it's interesting for astrobiology, is that it's very much like the early Earth, the primordial Earth. It's the only moon with any type of atmosphere that's actually got more atmospheric pressure than the Earth itself. But what the real thing about Titan that's cool is it has liquid on its surface. And that's like the key for astrobiology, is liquid on the surface, but typically liquid water. The thing with Titan is it's not water, it's too cold. It's like negative 300 degrees. So what kind of water, what kind of liquid is it? It's actually liquid methane, CH4, or ethane, and it has all of these hydrocarbons that are in the liquid form. And so scientists think that Titan could possibly host life that's different than we think, maybe, because it has liquid, but it's not water. This is a little bit of the atmosphere of Titan showing in the globe. And so Titan is a really interesting planet for astrobiology. And we're going back to Titan with Dragonfly. Humans are going back in like 2030 or something like that. Very, very soon. It was NASA approved it to explore these lakes, and it's going to have another little helicopter as well, which will be really exciting. So the Huygens probe landed on one of the solid parts of the surface to look at, they were hoping to land in a lake, but they didn't, and to explore. So now we know that this is the only other surface in the solar system besides Earth with any type of liquid on the surface. So it's really, really interesting. And I'll probably skip, okay, so let me, what time? Am I good? 10 minutes? Okay, 5 minutes? Okay, 10 minutes, all right, so in 10 minutes, let's just talk a little bit about beyond Earth. And I'm going to zoom out, and here's our solar system again. And what I'm going to do is I'm going to turn on what's called the radiosphere. And I'm going to turn on, while we see that, I'm going to turn on the exoplanets. So these are exoplanets, if you don't know, are planets that are outside our solar system. And I have two data sets in OpenSpace to show you. So the radiosphere and exoplanets. And I'm going to zoom out to where we see the radiosphere so you get a sense. Okay, so the radiosphere is as far as we've sent signals out to space. While the Voyager spacecraft, and I'm going to talk a little bit about Voyager. Voyager is the farthest probe we've sent, but it's not even beyond the solar system. It has 30,000 years to go. And by the way, to get to Alpha Centauri, which I think was part of the will take 70,000 years just on Voyager. And we can't even, that's as fast as we can go. That's 1 million miles a day since 1977. So that tells you something about how fast we can go. The radiosphere, and Earth's in the center of this, by the way. Actually, Titan. Yeah, let me go back to, let me center on Earth. Okay, so Earth's in the center. And the circles you see are locations of our nearby exoplanets. And inside the sphere are within 100 light years of Earth. And the yellow dots are Kepler. The Kepler mission is provided some data within 300 light years of Earth. So this is as far, this sphere is as far as we've sent radio signals, television, inadvertently just because we broadcast. These are not intentional signals, but they're going out. But this is as far as they've gone. And when I zoom out at the end, I'll show you how far that really looks in comparison to the entire universe. But I'll just say a second about exoplanets. We think of them, we see pictures, you may see illustrations like this, Earth-like exoplanet. These are planets that are rocky and close enough to their star that they could have liquid water on the surface. So then artists do these renderings, and they look very beautiful, but we don't have any pictures of them like this. We only know them by these locations. And the pictures, the actual images you get of an exoplanet are like little tiny dots. We have no way of getting a closer image. But I will say that since Kepler, I meant to make this bigger, sorry I didn't. But this is Luke Skywalker on Tatooine. This is science fiction, I am aware. But there are two suns. And what I was going to say is that back in, I guess, 77, was that right? With Star Wars, this was thought to be science fiction. But now we know two suns is really common, more common than one sun. So something like this could exist out in the Milky Way and beyond. It's quite possible. And so what was once science fiction is now known to be reality in terms of the number of stars, and we're really pushing that boundary now of what we can understand nearby. So this is a little illustration of the Kepler mission, which was retired a few years ago. And how it worked is essentially that a planet would go in front of its star, going here from left to right. The light would dip in front of the star as the planet went across, and that's how they would know that a planet was there, and also tell the size of the planet and how far away it was. It's called the transit method detection, because the planet transits in front. And that's how Kepler worked to try to find Earth-like exoplanets. And it actually found lots of exoplanets. So we know from Kepler that from this mission that there are billions of planets like Earth possibly in our own galaxy. And then of course there are billions of galaxies, so there's quite possibly a planet just like Earth. And then I'll just say a second about Voyager. This was that mission I was telling you that that was supported by the Infrared Telescope Facility that we now use for astronomy. What I love about Voyager is that Carl Sagan was a real proponent of SETI, the Search for Extraterrestrial Intelligence, and he was not only a scientist, but he, as you know, publicized astronomy and was really interested in SETI. And what he did is he put on Voyager, on the probes themselves, these golden records. This is the front and back. And so each probe has a record, and on the record are sites, images of Earth. They're all scratched in binaries in code. Images of Earth, sounds of Earth, languages, music, all this time capsule from the 1970s sent to space, and he knew that we will never know if anything found it, because there's chances are basically zero that there's intelligent life near us, and we are limited by the speed of light, and that means that in 1,000 years, it will be 1,000 light years away, and there's probably nothing that can fly within that distance. And so in 1,000 years, maybe something would find it. That's how you think 1,000 light years away. But chances are, any intelligent life is much, much farther away, so we'll be long gone by the time anything, if anything, will find it. Anyone, any something. And then on the back are directions of where we are, our location in the galaxy, and some other indications that we're not dumb idiots, I guess, and directions on how to play the record and get the information for extraterrestrials. That's what Carl Sagan did. I think that's the last image. Oh, and then he turned it around. This is another important. He turned it around to look at Earth, and this is the pale blue dot that you may have heard of, where he saw this Earth like a piece of dust in a sunbeam of the sun. And he turned Voyager around, and this really gave people a perspective of how small we are. And there's a great poem, a great essay he wrote about how we are so, all the arguments and wars and everything we've ever experienced in our entire existence is on this tiny little dot, which is smaller than a pixel. And so it gave a whole new perspective about life on this planet, protecting the planet. He was a very big proponent about protecting this planet. And so this was a really critical image, kind of similar to the images we got from the moon, and really put in perspective kind of how we need to preserve their little dot and maybe put things in a better light for humans. Okay, so that's all of the pictures, and I'll just zoom out for you and just show you, this is our radio sphere. Remember, we're not even out of the galaxy. This is how far we've sent signals out to extraterrestrials. This is our galaxy. Our one galaxy. This is our radiosphere, and Earth is a tiny little dot in the center of that blue ball. And then if you go out, you see these galaxy clusters and galaxies, and now we're going out, we're hundreds of millions of light years away. And if you keep going, you'll end up at the edge of our visible universe, which is the cosmic microwave background. This is the limit of what we can observe. You'll see here, this is the leftover remnants of our Big Bang. This is 13.77 billion light years away now, that I just did in about 10 seconds, I guess. And so it's not a sphere. I know it gives that impression because that's what the software can do. But this is the leftover heat from the Big Bang. This is all we can see. We don't know if there's anything beyond it because we can't see. And light left this 13.77 billion light years away. So that's our Earth, that's our galaxy, and we're zooming back, and these are all the galaxies, our neighbors. Maybe there are other universes, who knows? But again, we have no evidence for life except Earth itself, which is pretty interesting. All right, so that's kind of all I was going to show. Does anyone have any questions or anything? That's it.